So thank you, Ethan. First of all, I would like to thank the organizers for the invitation. And so today we presented joint work with Alex Abreu and Matteo Secco. And I will talk about tropicalizations of moduli spaces. In particular, I will focus on moduli of roots. And this is my outline. And so my starting point is to introduce a little bit the theory that is behind these tropicalizations of moduli spaces, focusing on moduli of curves, which is the very first case one can consider in the theory. So this is the basic object that already appeared in Renzo's talk. So MGN, so the moduli space of smooth and pointed curve of genus G. This is not a compact space, so in order to get a compactification of this space, as Renzo mentioned, we have to resort to stable curves. So a stable curve is simply a nodal curve with a combinatorial condition telling you that the curve should have a finite number of automorphisms. And so if we consider MGN bar, which is the moduli space of n-pointed stable curves of genus G, then a famous result by the linear Mumford tell us that this is a projective scheme. So we have this very good and beautiful moduli space often considered in the literature. As I mentioned, I want to consider tropicalizations of moduli spaces. So I want to get a tropical analog of this space. And the tropical analog of this space is what is called the moduli space of tropical curves. So I want to introduce tropical curves first, to introduce the moduli of these objects, and try to see if there is any connection between these two spaces. So a tropical curve, so first of all, we can introduce the notion of metric graph. So metric graph is simply a graph with a length function on the edges. So for every edge, we have a positive real number. Sometimes a metric graph is given as the definition of a tropical curve. But for the purposes of this talk, we have to distinguish between metric graphs and tropical curves, which are the metric space associated to the metric graph. So each edge is indeed replaced by the interval of length prescribed by the length function. And so metric graph, sometimes I will refer to the metric graph as to the model of the tropical curve. Okay, so this, sorry? No. Loop, multiple edges connecting vertices. No, not direct. In a moment will be, yeah, multiple edges, parallel edges, and so on. So okay, so this is the notion, and we can also consider in some sense the analogs of the gadgets we had on an algebraic curve. So we can consider an n-pointed tropical curve, which is simply assigning n points on the tropical curve x, and we can consider the weights. Namely, I can consider for a finite set of points some positive integers or non-negative integers, and these are the equivalent of the genus of the components of an algebraic curve. So we have a n-pointed tropical curve with a weight, and the notion of stability, which is in some sense the tropical analog of the stability for algebraic curves. So this is the condition that should hold for every given point of valence at most one. So for example, if I draw this tropical curve, So it is a graph, and I have to put some length function on the edges. This is a stable tropical curve. I can put here genus 0 and 0. It doesn't matter. It satisfies this condition. But if I take this tropical curve, for example, and I put here genus 0, it doesn't satisfy this condition. So this is not stable in this context. Okay, I have to give more definitions. So there is already an interplay between algebraic curves and tropical curves. And the first step to do this interplay and this comparison is the dual graph of a nodal end-pointed curve. So for every given x is an algebraic curve. So we have components of this curve, and we can consider the dual graph of this curve. So the dual graph is simply the graph whose vertices are the components of the curve, and the edges are the nodes. And so the rule is that two vertices are connected by an edge if the corresponding components meet at the corresponding node. As I told you, this is the first approximation because, as I told you, a tropical curve is a graph and a length function. So out of an algebraic curve, we have a graph. We don't have a length function on the edges, but we have the graph. Okay? And we have the stability condition also on graphs. And actually, this is the same condition I told you before. The only difference is that this must hold for every vertex. And actually, an algebraic curve is stable if and only if its dual graph is stable. This is the rule that tells you that there is a very strong similarities between these objects, the algebra geometric object and the combinatorial object. And finally, I need this notion of specializations of graphs. So I say that a graph, I mean, this is a tropical curve. I erase the lengths on the edges. It becomes a graph. Specializes to another graph if the second graph is obtained by contracting one of the edges. For example, here I'm contracting this edge, and I have a contraction from this graph to the other graph, to the below graph. So the two edges becomes two loops, and this other edge stay the same. Okay, so these are the fundamental definitions I need to now state and introduce this object, which is MGN tropical. So as I told you, I wanted to introduce a tropical analog of the modular space of curves. I introduced the notion of tropical curve, and so it makes sense to introduce the set. So far is only a set of classes of stable and legged tropical curves of genus G. So this object, it is not clear so what type of structure we can put on this set. And so a first approximation to give you a structure is to describe what are the tropical curves having a fixed underlying graph. So if I want to parameterize all the tropical curves having gamma, a fixed graph as underlying graph, I only have to vary the lengths on the edges. So I can take this R to the E of gamma and positive because we want only positive lengths on the edges. But we have also to mod out by the automorphism group of the graph because here I'm considering classes of tropical curves. So this is, in some sense, the first step we do to construct a modular space of tropical curves. This is a cell parameterizing all tropical curves, classes of tropical curves, with a fixed underlying graphs. And if you want to put everything together, varying the graph, of course, what we can do is to consider this set. So this is a set, the union over all stable graphs of genus G. This has also a very nice structure, which is a structure of generalized cone complex. So a cone complex is actually a topological space obtained by gluing cones together along faces. And this generalized stays here because we are considering not just cones, but cones modulo a group, a finite group. So these are quotients of cones. And it is a theorem by Brunetto, Melli, and Viviani that this is, in fact, a generalized cone complex. The terminology they used was not the generalized cone complex. They used the word Stechifants, but I think nowadays everybody calls these objects generalized cone complexes. Okay, so this is nice, and I will tell you more about the rule you have to use to glue these cones together later on. Okay, so how these quotients of cones glue together will be clear in a few minutes. Okay, but as I told you, so just to sum up, we introduced the modular space of curves, the modular space of tropical curves, and now we want to see what are the similarities between these two spaces. And these objects already appeared in Renzo's talk. So the stratifications are very important in tropical geometry. So on one hand, we can consider strata inside the modular space of algebraic curves, which are the loci of curves whose dual graph is a fixed graph. And this gives you a stratum that I'm going to call delta gamma. And on the tropical side, we can do the same to consider all the tropical curves having a fixed graph as the underlying graph. And these are the cells I already mentioned before. There are the blocks to construct MGN tropical. So there are some naive similarities between these two stratifications. In a sense, they are dual. So the codimension of one stratum is equal to the dimension of the other stratum. But more than that, we have this very nice description of containments of strata. And the containments of strata is described by the specializations of graph. So whenever I have a specialization of one graph to another graph, I have that the corresponding strata are contained one in the closure of the other. And in the tropical side, it happens the same, only that we have to reverse the inclusion. Okay, so whenever I have a graph specialized into another graph, I have this inclusion of this quotient of cone into the other quotient of cone, the compactification, no, the closure. And so this is exactly the rule I use to glue together all these cones. So I can present in this way a phase inclusion of one cone in another cone. And I use this rule actually to construct the modular space of tropical curves. So they are, to sum up, cones, quotients of cones, glued together along phases. And this is the rule I use to put everything together. Okay, so this is MGN tropical. And actually, the precise statement about the tropicalization is given by the following theorem due to Abramovich-Caparoso-Payne. So it tells you that there is a natural tropicalization map going from MGN analytification. So this object comes from the theory, Berkovich theory. And so I can give you here a very rough definition of the space. So these are the map going from spec R to MGN bar, where R is the evaluation ring of a known Archimedean field. So you have to think about this space as the space of all one-parameter families of curves over this spec R. So the one-parameter family is obtained by pulling back the universal family over MGN bar. And so it is quite clear how to define a tropicalization map going from this space to MGN tropical. Why? Because if I have a one-parameter family over over spec R, I can take the special fiber. So the special fiber is a stable curve. The stable curve gives you the dual graph, a graph. And I miss the length function to get a tropical curve. And the length function is given by the local equation of the family. So the local equation of the family locally around the node is of type xy equal to f, where f is an element of R. I can take the evaluation of this element. It gives me a positive real. And so with this rule, we get a tropical curve out of an element of this space. So this space is quite difficult to introduce in the right way. So I want just to give you the rough idea. But it plays a very important role in the Berkovich theory of an identification of spaces. And on the other hand, this Abramovich-Caparoso-Payne theorem tells you that we also have a very famous and distinguished subset here, which is given by the skeleton of this space MGN. And again, I can just write, there is a distinguished subset of this identification. It is called the Berkovich skeleton of the space. And I can give you a rough idea of what the space is. This is, again, a generalized complex given as follows. So W is the strata of a stratification. And sigma W are cones. And HW are some groups that I don't want to introduce. But in this way, I can present this distinguished subset, which is the skeleton of the identification space, as a generalized complex. And these are the cones that are used to describe this space. And the Abramovich-Caparoso-Payne theorem tells you that this space can be identified with the modular space of tropical curves. And we also have a retraction map from this space to the cone, to the skeleton. And actually, the incarnation of this retraction is given by the tropicalization map. So to sum up, this theorem tells you how to describe in a very modular way, in a very clear way, what is the skeleton of this space, which is actually MGN tropical, and the retraction map that becomes the tropicalization map. Okay, this is, in some sense, why this theorem was so successful. And I want to stress that later, a natural question was, okay, what happens with other modular spaces? I can repeat this statement for other modular spaces. There are many modular spaces that have been analyzed. Sometimes this theorem can be stated exactly the same for other modular spaces. Sometimes no. It depends. And today I want to introduce moduli of roots of line bundle and see whether or not we can reproduce this theorem for this new modular space. So the tropicalization of this modular space. And what is this modular space? So let me just introduce SGN-R. So this is the space I want to consider today. It is the space of smooth curves and together with a root of a line bundle. So first of all, I can consider the trivial bundle or the dualizing sheaf, or the more general case, I can consider R root of the dualizing sheaf to the L twisted by the points you have over the modular space of n-pointed curves. This is the more general case I can consider. So actually, these are all the universal line bundle I can consider, I guess, over MGN bar. And As for MGN, we can consider compactifications of this space. There are a lot of works that have been done for compactifying this space. And in particular, I don't want to enter in details. For the purposes of this talk, I don't need the modular description, but only I want to recall here that a bunch of people compactified this space in many ways. There are different compactifications. And I'm going to call this SGAR. So A means that, I can put all the relevant combinatorial data in a tuple and call this space SGA. There are few remarks I want to make about these spaces. They are et al. Over the smooth locus. But more than that, for this talk, it is very important to recall that these spaces are not irreducible in general. So, for example, if I consider the moduli space of square root of the trivial bundle, we already have two components. One is clear, which is so I can fix the trivial bundle as square root of itself. And the other component is the prime variety, the moduli of primes. Or we can consider the square roots of the dualizing sheaf. Or again, here I have two components, and they are very well understood. They are the components corresponding to the parity of sections of the line bundle that I'm considering. These are the modular space of theta characteristics. There are these two components. And so keep in mind that they are not irreducible. Okay, so these are important things. So I want now to go to the tropical side of the story for roots of line bundle. And to do that, I will introduce the tropical analog of what should be a divisor, a line bundle. So for me, the tropical analog will be, first of all, divisors on graphs, and then on tropical curves. So a divisor is simply on a graph is simply a function going from the set of vertices to the integers. And I can also define what a universal divisor is, because I recall you that we have this universal line bundle that I want to square, and now I want to define a universal divisor for graphs and tropical curves later. And this is the rule that I use to define the universal divisor on a graph. Actually, this is the multi-degree of that divisor, of that universal line bundle, which was omega twisted with some points. This is already clear that this is the multi-degree of that line bundle. This is here we have an example of this universal divisor. And from the tropical side of the story, I have also the notion of divisor. Is simply, as for a graph, is simply a function from the tropical curve to z, except that I impose the condition that only for a finite number of points, this should be non-zero. And I can consider also the universal divisor on tropical curves, because if I have a divisor on a graph, I can consider naturally a divisor on the tropical curve having that graph as model. So these are the important things I want to define. And now I can state our problem finally. So what is our problem I want to consider today? So for any relevant combinatorial data, I want to construct a parameter space for what? For pairs. X is a tropical curve, and D is the class of a divisor, which is such that R time this divisor is the universal divisor. So this is the equivalent of the root of this divisor, or the divisor for tropical curves. And so we want not only parameterize the tropical curve, as we did for MGN tropical, but also this root of the divisor. And as expected, we want to to see if the theorem due to Abramovich-Caparoso and Payne still hold for the case of this moduli space of roots. So the solution here is the following. I want to consider and construct a tropical moduli space. So I want to codify, I want to encode all the combinatorial data that comes from the problem in a pair, gamma and phi. Gamma stay for the curve, and phi is a mysterious datum that I don't want to introduce now. But to construct a modular space, a tropical modular space, this data should be compatible with specializations. This is important because we want to glue together cones to get a tropical modular space. So this is important. And also, it is important for the modularity of the space that this gamma should recover a tropical curve, or all the tropical curve having gamma as a model, but n phi should recover a root of the divisor. So these two elements should recover the pair x and d on a tropical curve. And so what are the relevant combinatorial data that I want to emphasize here that reconstruct, in some sense, the roots of a divisor on a tropical curve? So this is done by the notion of flow on a graph. So what is a flow? So a flow with modulo r, actually, is simply a map going from the edges of a graph to z modulo r. So here I have an example of flow. So these 2, 1, and 0s on the edges are a flow. And I have also to introduce a choice of an orientation on a graph to have a flow. And what is important is that I can define a divisor out of a flow. And the rule is the following. I take all the contribution on the entering edges, the edges that are entering the vertex, and the contribution of the edges that are going out the vertex. So for example, in this example, I have a 2 and a 1, 2 entering and 1 going out. So I make here a 1. 2 are going out the vertex, so I have a contribution 2 to the divisor, and so on. So it is clear how to construct a flow and its associated divisor. And this plays a very important role for our theorem. This is the set of all flows. So I can fix a divisor on a graph, and I can take all the flows whose divisor is a given divisor, modulo r, of course. So if I start with 1, 1, and 1 here in the picture, I get here -2, 1, and 1 for the divisor associated to the flow. But modulo 3, for example, these two divisors, 1, 1, and 1, and the other -2, 1, and 1 are the same. So actually, this flow becomes inside this space, F, R, gamma, and R. So just to sum up, I wanted a combinatorial way to recover roots of divisors on a tropical curve. I just introduced flows. And actually, I have a theorem telling you that this set of flows, the set of flows F, gamma, and D, is indeed the set of all R roots of the divisor D. Indeed, we have a bijection between the set of flows and the set of these roots, actually the classes of these roots. And this correspondence, this one-to-one bijection, is indeed very explicit, and we can describe explicitly what is the root associated with flow. This is the rule. For example, in this example I had, so 2 and 1 and 0 was the flow. And so I have -1, and 0 that are computed by this formula. And I stress here that to put some contribution on a point inside the edge to everything works out. And so the rule is that I put 2, which is exactly the value of the flow at distance 1 over r from the source of the edge. So 1 here, this 1 on the edge, goes to a 1 at distance 1 over r from the source of the. And so with this rule, I can state that this, which is this delta d phi, is actually a square root of the initial divisor. So I mean, 3 times this divisor doesn't seem so much this divisor, but there is an equivalence relation. So actually, this 3 times this divisor should be equivalent to 1, 1, and 1, and it is done by a sort of cheap firing on the tropical curves, so everything works out. Okay, so this is a nice theorem. Actually, this is quite subtle theorem because we had to prove all the independence on the orientation. So a lot of things are behind this theorem. But this resolved the problem for a fixed tropical curve. So for a fixed tropical curve, this space of flows solve the problem that to codify, to encode all the roots of a fixed divisor on a tropical curve. And now I want to cast everything together on a universal moduli space. And this is done by means of a poset. So I can consider the poset of all graphs, stable graphs with n legs of genus G, and a flow whose divisor is the universal divisor. And this is a poset because we can order these pairs. I mean, I can consider also specializations of these pairs in a very natural way.
What is the specialization of the flow?
Yeah, I mean, if I have a flow here, 2, 1, and 1, just forget the edge that is contracted. Okay? Just forget the edge. And actually, we can also do the same for that we did for MG tropical. We can put everything together. So we can consider these cones mod out by the automorphism of the pairs. And we can glue these together along phases whenever I have a specializations of pairs. And I get a generalized concomplex. So this generalized concomplex should parameterize the roots of the divisors, of the universal divisors on tropical curves. And indeed, we have this theorem. These points actually parameterize these pairs of a tropical curve and the root of the universal divisor. It is connected through codimension 1, which is a very natural property that is expected by tropical spaces. And I also have a forgetful map from this space to MG and tropical. And the fiber is what you expect, actually. It is the set of R roots of the universal divisor modulo the automorphism of the tropical curve. So from the tropical side of this story, everything works well. Actually, we can construct a modular space, and fine. It parameterizes the things you want to parameterize. And the question now is, what is the relationship between this space and the space, the algebra geometric space, as GAR? Okay, so I want just to recall you a fact that I wrote here. This skeleton was actually the union of this strata, and I have a strata for every given, I have a cone for every given stratum of the moduli space. So in some sense, here the combinatorial while MG and tropical, I recall you, was the union of a bunch of cones modulo automorphism. And what I want to stress here is that we already have a bijection between these two objects, because when gamma runs through all stable curves of genus G, you have all the strata of the moduli space. So it is crucial for these two spaces to be isomorphic that I have a bijection between strata and these cells appearing in the modular space of the tropical objects. And so I mean, this is the statement. To each stratum, we have an associated combinatorial type. But what happens for the roots is that we don't have this bijection between the strata of the tropical space and the stratification of the space, of the algebraic geometric space. And I want to recall, indeed, that, I told you to retain this property of the modular space of roots, that they are not irreducible. While what is the most degenerate stratum I have in this space? When gamma consists of only one vertex, I can only put one flow on this graph, so I have only one stratum corresponding to a graph of one vertex. So it can't be that we have a correspondence, bijection between the stratum and the stratum of the algebra geometric space and the strata of the tropical space. And indeed, we have this statement. We only have the tropicalization map. And when restricted to the skeleton, we only have a surjection between the space, the analytification, restricted to the skeleton, to the modular space of tropical roots. And in fact, for example, as I told you, this space is always connected, while we have cases where the modular space of roots in algebraic geometry wasn't connected. And so this theorem also actually reminds the theorem for admissible covers, and is actually the same case that we can't copy the statement of Abramovich-Caparoso-Payne, but we have this weak statement. Yes?
Is it the case here as well that while the map is not isomorphous, it is when restricted to an individual code, or does it get even worse?
Is the case what? Sorry?
Restrict to an individual code?
Yeah.
It is an isomorphism. Does it multiple codes mapping to
yes.
You get worse behavior?
No. It's the same. I mean, I think this is the meaning of surjective morphism, maybe of generalized complexes. And I have a few minutes, maybe. So it stays not clear how to refine, actually, the combinatorial data to give more cones in the tropical side, and hopefully to give you an isomorphism between the skeleton and the tropical space. So you can try to enrich your combinatorial data to get a more finer tropical space, and hope to be isomorphic to the skeleton. And actually, we did that for the case of the modular space of spin curves, which compactifies the modular space of theta characteristics. And actually, we can consider not only flows, but flows and the sign function on this gamma modulo gamma. I mean, this is I don't want to enter in details, but it's a refinement of the combinatorial data we had that actually are considered and that mimic the parity of the section of a line bundle on a theta characteristic. And so we can do the same. We can construct this modular space. Again, this way with this richer combinatorial data. Here I remind you that there is this nice compactifications due to Korn-Alba of the modular space of spin curves. And actually, a theorem that we proved is the following. This is actually the same statement proved by Abramovich-Caparoso-Payne, and tells you that actually the tropicalization map can be defined, but also that the skeleton of the space is isomorphic to the modular space of tropical spin curves. So in this case, we got a refinement of the combinatorial data, which was enough to recover the skeleton of the space. But it is not clear how to do that in general. So already the case of a square root of the trivial bundle, for us it is not so clear how to get this finer combinatorial datum. I mean, maybe you can try to do when to define a triviality of the line bundle, but so far when you go to the stratification, it's not so easy to prove that this combinatorial data describe entirely the stratification of the algebra geometric space. And so actually the general case seems to be quite challenging, and I don't know, there should be a refinement of this combinatorial data that allows you to describe detropicalization in the right way. So I think that I will stop here. Thank you very much for your attention.